Ladies and gentlemen, welcome to the Hong Kong IE Civil Division event, technical webinar on full waveform inversion for leak localization in water pipe networks, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm MC of today's webinar. We are honored to have Dr. T.C. Che, who is a research assistant professor at the Department of Civil and Environmental Engineering in PolyU. He obtained his PhD degree from PolyU in 2019. During 2021 and to 23, he was a faculty member at He University. His research interests include fluid mechanics, wave dynamics, data assimilation, and inverse problems. He is also a editorial board member of engineering applications of computational fluid mechanics. Without further ado, I would like to invite Dr. Che to deliver the talk today. Dr. Che, please.
Fiona, can you hear me?
Yes.
Okay. Thank you very much for the introduction, and good afternoon, colleagues, and good afternoon for the online audience. First, I would like to thank the HKIE and our CE department for the invitation. And so before the technical session, I would like to promote our department a little bit. So the name of our department is Department of Civil and Environmental Engineering. Usually we call it CE for short. And actually our department has a very time-honored history. I think last year we just celebrated our 50 years anniversary. And actually our department performs very well in the subject ranking, like for the QS ranking, we ranked the 14th in the civil and structural engineering released this year. This is #1 in Hong Kong. And also for the Shanghai ranking, the Shanghai ranking is the Shanghai academic ranking, and we rank the 3rd in the civil engineering, and the 2nd for the transportation science and technology. So both of them are #1 in Hong Kong. So there are also lots of famous professors in our department, like we have our president, Professor Jin Guangteng, who is the member of Chinese Academy of Science. And we also have 7 Changjiang scholars in our department. And we have 28 professors among the world top 2 percentage scientists released by the Stanford University, I think, last year. And also in terms of the funding application, we perform very well. This is probably the biggest research scheme in Hong Kong, the same-based research scheme. In the recent 7 years, we got 4 projects. You can see the funding ranges from 30 to 60 million Hong Kong dollars. It's a 5-year research project. I think this 2 is about the structure, and this 2 is about the atmospheric science. And also we have like 30 laboratories in our department. They almost cover all field of the civil and environmental engineering. So there we have different levels of programs, like we have 1 UG program, and we have 2 TOD PG program. So 1 focus on the civil and 1 focus on the environmental. And we also have the research PG programs, like the 2-year research-based master degree, the Master of Philosophy, and also the 3-year or 4-year PhD degree here. So this is only a very brief introduction to our department. So you can visit our web for more information on our department, or you can follow our social media channels like the Facebook, like the YouTube here, and also for the WeChat and Xiaohongshu here. So let's start our second part, that's a technical session here. So today I will talk about the leak detection in water pipe networks using waves. And actually, probably there are some technical issues, but I will make it general so that all audience can learn something from this talk. So in the final, if you have any questions, we can discuss in the Q&A session. So today, I think the first two parts are very general. It's about the wave-based leak detection method. I think if you are from the structural healthy monitoring, or from the imaging, or from the source reconstruction field, you can learn very well here. And these three parts are kind of technical. I will introduce the waves and for leak detection in tree and loop networks. And finally, we will deal with the ill-post inverse problems, because sometimes we have the matrix inversion, which is ill-post. I will also talk about that. And lastly, I will talk about our ongoing work. It's about the data assimilation method. So you can see this is our urban area. Probably every day you can see some structures above ground, like the buildings, like the road, like the traffic, like the gardens. But there are also lots of important structures underground, like the water supply pipes of our city. Usually, in Hong Kong, probably the water pipes have been buried underground for like several decades, or even more than 100 years. So aging is quite a severe problem of these water supply pipes. So if we take a close look, they suffer from the leaks. Each day, 30% of the water is lost from these leaking pipes. Probably the deformation here, probably there is a ground settlement. So our pipe may deform. The shape of the cross-section area may change. And also for the corrosion, especially for the metal pipes. And also, you can see here, we have blockages. And we focus more on the leaks. Nowadays, there are many different methods for leak detection. And you know, a leak on the pipe is pretty much like a leak on the pipe. It can generate some hissing noise, like the sound. So the idea of the listening stick is that the closer to the lake, the stronger noise will be heard by this guy, so that the lake can be localized when this guy hear a very, very strong noise. This is the idea of this listening stick. Actually, this method is very old, but very popular. But it's because it is very easy to implement. Actually, very similar for the smart ball. The smart ball is pretty much like a sensor that moves with the flow within the pipe. So you can see here, if we release the smart ball here, it can move with the flow. It can monitor the noise within the pipe. So you can see here, the noise level is not that high. So when it reach a lake here, you can see here, it has a very strong noise. Probably it moves forward. Here, some air bubbles. Air bubbles also generate some noise. So you can see here, the noise level here is very high. But there are drawbacks of this method, like they are passive, and they are very slow. They are very slow, and their detection range is very short. And for this kind of smart ball, and if this smart ball flows to a pipe with smaller diameter, it may become blockage. so it can cause additional problems. And also, usually the pipes are underground, but near our road, there are also lots of traffic noise may influence this method. So you can say, so although people are using this kind of method, so there are still lots of leaks in our networks. So that's why we wanted to propose some more efficient and effective method to localize the leak. So you know the waves are all around us. you hear me because of the acoustic waves, and our phone works with the magnetic waves. So in nature, actually the animals are very smart, and if there is an unknown object like this mouse during the night, or the fish in the deep ocean, because they cannot see the fish, but they are very smart. They usually send a wave, and they can get some reflection from these small animals. So they use the reflection waves to locate and identify the object. So that's the idea. Probably I think here is a MP3. If you can hear, this is okay. Probably I need to change the pointer. First one, yeah. Here is the sound generated by this bat. You can see right here. This is a low frequency wave. This is a high frequency wave. Actually, the animals are very smart. They generate waves at a different frequency. So you can see the sound generated by this whale for the low frequency wave. Higher frequency, even higher frequency. Okay. So actually, the same idea has been used in the ocean acoustics. It has been used in the ocean acoustics here. And people usually send a wave into the ocean, and they get some reflections. And they, based on the wave physics, they can get the imaging of the ocean bottom. They can localize the fish or the submarine here. That's the basic idea. The question is, can we do the same in pipe networks? The answer is yes, because we have the Wertheimer waves. Probably I can change a pointer here. Yeah, use a laser pointer here, because we have the Wertheimer waves in our pipe system. Actually, the Wertheimer wave is also one kind of acoustic wave. The wave speed is very high. It's like 1 kilometer per second. So pretty much like in this system, here is a reservoir. We transport the water to this valve by this pipe. So if there is no leak in the pipe, and we send a wave here, you can see the wave propagate and reflect at a boundary. And we put a pressure sensor here to measure the pressure. We can measure this kind of signal. And if we transfer this guy into the frequency domain, we can get the frequency response function. And these are the reference peaks of the system. So if there is a leak, still we send a wave here. You can see the wave propagate and will have additional reflections from the lake. And we still measure here to get the time and frequency domain signals. You can see it's very different from the no lake case. So based on the measured signal, actually people develop different algorithms to find out where is the lake and how big it is. That's the general idea of this method. So before getting into the technical issues, I wanted to talk about something about forward and inverse problem. Actually, usually we have a model in our numerical simulation, and also in the lab experiments, we have a model. And if we know the parameters of that model, we can get some data. So that's the forward problem, because we know the P, we know the parameter, and we know the model. We can generate the data. That's the forward problem. The forward problem, the purpose usually being to the prediction or to understand the physical mechanisms of a process. That's the forward problem. But usually sometimes we don't know the model parameters. Although we have the model, but we don't know the model parameters, but we have some observations. So if we know the model and we know the observed data, and this guy is unknown, we want to determine the model parameters. This is the inverse problem. So I don't know if I can remove this guy here. Cannot. Okay. This is actually our time domain signal. This is our frequency domain signal. And actually, our wave-based lake detection method have been developed for like 20 or 25 years. So there are many different kind of methods, but this method can be classified into two main types. The first type is local feature-based method. The local feature-based method only use a partial information, the partial information of the measured signal to localize the lake. Like for the reflection-based method, the reflection-based method only use the first reflection here. You can see here. Here is the reflection from the lake. And if we know the occurrence time of the first reflection, and we know the wave speed, so we can determine the location of that lake. So you can see only this local information is used instead of the whole time domain signal. For the FRF peak pattern-based method, this method only use the random peaks. You can see we have the frequency response function here. You can see these are the random peaks. So if there is a lake, you can see there is a drop on the random peak. So there is a certain pattern. So different lake location will generate different pattern. So you can see the peak pattern-based method only uses the random frequencies instead of the all frequency information. So we call it a local feature-based method. So one drawback of the local feature-based method is that the information used is very limited. So if there background noise, it can be easily disturbed by the background noise because the information used is very limited. So the local feature-based method is not robust, and the accuracy is very low, usually very low. And the second method is full waveform inversion method. And based on the name, you can say the full waveform inversion method uses the whole measured signal, like the ITA. This method uses the whole time domain signal. Actually, this method matches the measured signal with a numerical model. In that numerical model, both the lake size and the location are free variables to be optimized. But this method is very time-consuming because we cannot separate the lake size and the location in that numerical model. So the efficiency of this method is very, very low. And for the mesh field processing method, we use the entire frequency domain signal to localize the lake. Actually, here we use an analytical model. And in that analytical model, actually we separate the lake size and the location so that we can estimate the two unknowns separately. First, we find out where is the lake, and then we estimate how big it is. So you can see the efficiency of this method is very high. So you can see here it's robust, accurate, and efficient. That's why we use the metric field processing method in our following topics. And actually, this is our the model we used in our problem. You can see here is a single pipe system. You can see here is a reservoir, here is a pipe, here is a valve, and usually this is the upstream point. And if we know the discharge and pressure here, like the Q and H, if we know the Q and H here, we can compute the Q and H before the lake by multiplying this transfer function. It transfer this point to this point. Actually, this transfer function, we call it transfer matrix. It is a 2x2 matrix. And essentially, they are mass and momentum equations in the fixed domain. So you can say when we across this lake, when we also need the transfer matrix for the lake, and we can times the other matrix to move forward. And you can say eventually we can represent any Q and H and any measurement location. Here I neglect some tedious procedures here. So finally you can see we can get this is a lake induced pressure difference, delta H. It equals the lake size. This is lake size, SL, times G. G is a function that depends on the lake location only. So you can see we separate the lake size and the lake location. So we call it a factorized model. Yeah, because two unknown variables are separated. So for the MFP here, if we write our model for all frequencies, it is in this vector form. You can see here the delta H is the measured data, measured signal. And actually, this is our model. This is our model. The SL is unknown lake size, XL unknown lake location. The N here is a noise. So you can see our objective is to, usually we know the measured signal, but we don't know the lake size and the lake location. So our objective is to use this guy to determine or estimate the lake size and location here. And usually we use the MFP. Again, I neglect the tedious procedures here. So finally, because here in the model, they are separated. So in the inverse problem, we can estimate them separately. So first, we find the location for the lake, and then we estimate how big it is. That's the general idea. So this is our first topic. So this is our first topic. It's about the lake detection and wave propagation in the tree networks. Usually for the tree network, it means we have this kind of branch structure. And one feature of this tree network is that you can see from the boundaries, you can see this. It has a boundary here. It has a boundary here. This is our wave source. We send the wave here. You can see from the boundary to the wave source, there is a unique path, right? Also from here to here, there is a unique wave path. So based on this unique path feature, usually we represent the QH here by the linear superposition principle. Pretty much like for instance in this pipe network, if we know the QH here, we can by multiplying the transfer function from this point to this point, we can get the QH here. But when we cross this junction, we also need the flow from this pipe, right? So we can, because we can measure, actually we can measure the QH here. So using this transfer function to get the QH here. So we know the QH here, we know the QH here, we can use the mass and momentum equation at this junction to get the QH here. So you can say we can move forward. The idea is that when we across this junction, we only take the pressure head from one pass and take the discharge from both paths, because we have the continuity equation. The continuity equation, we should sum the discharge up, but for the pressure, we can only take one. You can take this one pressure, or you can take this one pressure. So again, I neglect some math procedures here. So finally, we can get this factorized wave propagation model. You can see it is pretty much like the single pipe system. You can see here the delta H, the lake size, times the Green's function. It depends on the lake location. This is the noise. So if we wanted to localize a lake in this network, we should know the boundary conditions. We should know the QH here. We should know the QH here. That means we need to put sensors here and here. But the pipes are all underground. Probably sometimes we cannot access this pipe. So at this time, if we cannot put a sensor here, then this method doesn't work. So yeah, if we cannot access to this pipe, then this method doesn't work. So then we modify the model. We modify the model. One key procedure is here. I neglect some procedures here. That simplification is based on the small lake approximation. So if we assume the lake size is very small, and we can neglect this term. So in this way, we derived a point matrix for this pipe. And actually, we looped all the information of this pipe into a point here. So when we across this point, there is no need to measure the QH here. We just across this point. This is a point matrix. Initially, it was a field matrix. It's a field matrix for this pipe, but now we derived a point matrix. So you may ask, how good is this small lake approximation? Actually, we did some numerical tests for different size of lakes. Yeah, this one is for a small lake. This one is for a medium lake. This is for a larger lake. You can see compared with the transfer matrix, our linearized model, they agree very well. And also we test more case. You can see here, this is as the increase of the lake size, the error also increases. But for a small lake, like here, for a small lake, the linearized error is very small, like 5% error. You can see here. Yeah, it is reasonable. And then we do some numerical test. And in this numerical test, you can see here is a reservoir. It supplies water to the valve here. We cannot access this pipe, so we cannot put the sensor here. So now we only need two sensors. We have this sensor and this sensor. And we also put some noise in the in the numerical test. Like the signal to noise ratio is like 10. And you can see here, these three are for the single lake. You can see here. So the vertical dashed line here is the real lake location. And the curves are the objective functions. So usually the higher the objective function, that means the more probability for the lake location here. So you can see here we find the lake. The objective function has a maximum value at the real lake location. This is in type 1, and also this guy is for type 2. This one is all for type 3 here. And also we also test multiple lakes, and if we put 2 lakes into the pipe, but the multiple lake only in the data, and in the model we only have 1 lake, because we found that the total lake induced pressure difference is the summation of all individual lakes. Yeah, so we can do this. We can do this like here. We put two very close lake in pipe 1 here. You can see our objective function only give one peak instead of 2 peaks, because they are very close. It is much smaller than the half wavelength we send. So this is because of the diffraction limit. This is our resolution limit. This is because of the physics. So if we put 1 lake in pipe 1 and the other lake in pipe 3, you can see here we can localize them successfully. But here, when we put a lake in pipe 2 and 3, in pipe 1, the objective function has a very high value, but this is a wrong value. This is because we only put 1 lake in our model. So our model cannot guarantee for multiple lake detection, we cannot guarantee we can localize that lake. The only thing we can guarantee is there is a local maximum value instead of the global maximums, because of the limitation of our model. Actually, we can address this problem by putting the right number of lakes in our model. This is a network with more pipes. Here, I think we have 7 pipes, and we also try a different number of sensors. Like if we cannot access this pipe, we get this result. If we cannot access these 2 pipes, we get this result. You can see here. For this one, we use all 5 sensors for this guy. And for this one, we use 4 sensors. This one, 3 sensors. This one, only 2 sensors. You can see no matter how many sensors we use, we can localize that lake. But if we use less sensors, you can see the saddle loop, we call the second peak. You can see the second peak here. We call it saddle loop. The relative length, the relative height of the main loop is very close to the saddle loop. But here, if we use 5 sensors, you can see here the relative height of the main loop is big. It's very evident. So that means as we reduce the sensor numbers, it becomes much challenging to localize that lake. We also test this method in the lab. Actually, this is the hydraulics lab in HQST. And in the lab, pretty much like our numerical case, here is I think here is a pump. Yes, here is a pump. the upstream boundary is a pump, and yeah, it's pretty much like here. Here is a pump. It has 3 pipes. The lake is in pipe 2 here, and we assume we cannot access the pipe 3, so we didn't put sensor here. We only put 2 sensors in pipe 1 and pipe 2, and the total length of the pipe is like 150 meters. The total length of the pipe. You can see actually we send a wave here. You can see this is the measured signal by these 2 sensors. You can see there actually some noise. There's some noise, and if we transfer, because it's a frequency domain method, and we transfer the time domain signal into the frequency domain, you can see at higher frequency they becomes quite noisy. So if I remember clearly, we cut here. We only use the first like 5.5 hertz. So you can see here is the detected result. This is the dashed line is the real lake location, and our maximum objective function is here. The error is pretty much like 5 meters. 5 meters. And the second topic is the wave propagation and the lake detection in this kind of loop network. And for the loop, we have this kind of structure. As we mentioned before, in the tree network, there is a unique path between any boundary to the wave source. But if you look at this loop network, here is the boundary, here is the source. From the boundary to the source, you can see here we have more than 1. So the wave path is not unique. There is a good point for this feature, because for the water supply, if you think of the water supply, probably for the tree network, if any one of the pipe is broken, probably if this pipe is broken, we cannot get water here. And also if the pipe 2 is broken, we cannot get water here. But for the loop network, if pipe 2 is broken, the flow can still goes in this way, and we can get water here. So you can see here, this kind of loop structure is good for the service of the water users, but it's not good for the wave propagation. So because you can see there are multiple wave paths between different nodes. So this makes the wave propagation between different nodes very complicated. So it's difficult for us to separate the 2 unknowns, the lake size and the lake location. It's difficult to separate in this kind of loop network. So that's the problem. That's the problem. So in the fluid mechanics problems, usually if we want to study a problem, usually we need to select the control volume. Like I think the control volume is pretty much like the numerical mesh you draw in your numerical model. It's pretty much like the mesh. So for a pipe problem, so how should we select the control volume? Probably we can select the control volume in this way. We can select this one as our control volume. We include the water. Probably we can choose a larger control volume to include also the pipe wall. Probably even larger control volume to include the soil outside. Probably we can draw some small meshes here. So for pipe problem, which volume should we choose? Do you have your answer? The answer is it depends. It depends on your problem, and it depends on your purpose. So if our purpose is the pipe flow, it's 1D if the purpose is to study the 1D pipe flow, we will choose the control volume A. So if we want to study the fluid structure interaction, yeah, the B is the best one. So if we want to study the fluid structure and the soil interaction, we should choose the third one. So if we want to study the 2D flows, of course, we should choose our control volume in this way. So you can see the selection of the control volume is very flexible. It's very flexible. So the main purpose is to simplify the problem. So if we want to focus on the pipe flow inside the pipe, if we choose this kind of control volume, the problem will become very complicated. So similarly here, for this kind of loop structure, usually people choose this kind of control volume. You can see if we choose this kind of control volume from the boundary to the wave source, there are multiple wave paths, which makes the problem very complicated. So can we choose the control volume in this way? Here we put two control surface here, like the S1 and the S2. And if we put two control surface here, actually the loop structure are broken. It becomes like a tree network. Here we have a boundary. Here we have a boundary. Here we have a boundary. We no longer have the loop network, as if the loop network has been transferred into a tree network. So our previous theories and models can be used here. But if we wanted to put control surface here, we should know the QH here. We should know because it's a boundary. We should know its property. There are two methods to do this. The first method is we can put the sensors here to measure the QH. But the efficiency is quite low, especially for larger networks. We cannot do it in this way. The second method is we can compute by computation. Probably we have some boundary measurement. Based on the boundary measurement, we can compute the QH at every node. That's the idea. Actually, that's what I did. That's what we did. Usually, for this kind of loop network, if we know the location of this lake, because now we wanted to compute the QH at every node, the QH here, every node. And now the number of the pipe is M. So you can see in every pipe, there are 4 unknowns, 2 upstream, 2 downstream. So the total number of unknowns is 4M. So how many equations we have? Like we have the mass momentum equation for each pipe. We have the mass momentum equation for the junction here, and also we have the boundary conditions. So if we sum all these equations, it's 4M. So the number of equations equals the number of unknowns. We just write all the 4M equations in this way. It is AX equals B. The unknown hydraulic properties are in the X, so we can very easily compute the X. So here we know the QH at any point. That means we can choose a control surface here. But there is a problem because if we know the location here, the size here of this lake, but usually it is unknown lake. If we don't know its lake size and the location, usually we have 2 more unknowns. Now you can see the total number of unknowns is 4M. and the total number of equations is 4m plus 2. So you can see the total number of equations is 4m. So the problem becomes underdetermined. So it's very difficult to solve this problem. And if we don't know the lake size and the location here, actually the lake size and location goes to the A, not X, because X is for hydraulic properties. It is in A. So you can see now both A and B are unknowns. Both A and B are unknowns. So it's also very difficult to solve this kind of problem if both A and X and unknowns. And because the lake location is unknown, the lake location, it is a sine and cosine functions. So it is in A, so it's a nonlinear. So if we have this kind of difficulties, it's impossible for us to solve this problem. So our idea is to, we don't want this equation. We don't want the mass and the momentum equation for the leaky pipe, for that leaky pipe. Instead, we measure, because initially we have one boundary condition here, we have one boundary condition here, but now we put sensors here to measure one more boundary condition and put it in our equation. So you can see now we have 4m unknowns and 4m equations. It is only the x is unknown, and it becomes linear. So we can easily compute the hydraulic properties at every node. So you can see here now we can break this loop structure and treat it as a tree network. Yeah. So you can see here, yeah. Here for this loop network, here is the reservoir, a loop network. We send the wave here. Now we put two sensors here and here. You can see here when the lake is in pipe 1, the vertical dashed line is the real lake location, and the curves are objective functions. Actually, you can see this is a mismatching, the mismatch between the model and the data. So you can see it is minimum at the real location. And also for other locations, if the lake is in pipe 2, we can find it out. And also for pipe 3, we can find it out. Also for the pipe 4. So, but now we didn't put noise here. This is a noise-free case because there is inverse computation. The matrix inversion, that we found that is a ill-conditioned problem. And I will talk it later on. And also, we also apply this method in this kind of with multiple loops. And here, actually, once we have the boundary measurement, we can compute the QH, the hydraulic properties, and every internal node. So you can see we break here, we break the loop here, and also we break the loop here. So you can see the loop network becomes the tree network. So that's very easy to deal with. So you can see if the lake is in, I think this one is in pipe 1, we can pinpoint. And if it is in a pipe 6, yeah, it is here. This one is here. We can also pinpoint that lake. And also for other, I think this guy is in the pipe 10. Pipe 10. This is in the pipe 13 here. It's a boundary pipe. We can find them out. So as I mentioned just now, because we needed to use the boundary measurement to inversely compute the hydraulic properties. So there is a matrix inversion. For the matrix inversion, probably the determinant of the matrix probably very, very small. So it becomes ill post-problem. Like probably we can, yeah, if we do the singular value decomposition, the SVD, we can decompose this coefficient matrix A here. Actually, the U and the V are singular vectors, and the sigma here, the diagonal, or the sigma here are singular vectors here. So if we do the SVD here, we can represent our solution by the singular vector and singular values, singular vector and singular value here, because the B actually the B include the noise-free B and the noise. And here, see here, this is the B noise-free is here. This is a noise. So you can see this term is the signal projection. You can see here, this is the noise projection. We project the signal and the noise into like n singular directions. But there is noise in our measurement. So once we have a noise, probably some singular values are very, very small. So if we divide our noise by a very small singular value, the noise will be amplified. It becomes very large. Just like in this figure, you can see at this frequency, the red curve is no noise. We have no noise. And the blue curve is we have noise. You can see at this frequency, the noise is amplified. Its amplitude is much, much larger than the range frequency, than the physics peaks. So actually the amplified noise will distort the overall shape of our signal. So if we use the blue curve to localize the lake, you can see here, this is the result. We can only search a wrong solution. You can see here, if there is no noise, that's the red curve. We can find it out. But if there is noise, the noise is amplified here. We cannot accurately localize the lake. So to solve the ill-posed problem, people usually use the Tikhonov method to regularize the ill-posed problem. I think Tikhonov method is also popular in machine learning, I think, to avoid the overfitting. So, but there is a very important assumption for the Tikhonov method. That's the discrete Picard condition. It says that the coefficient, actually it is the upstairs here. This coefficient should decay to 0 faster than the singular values. So this guy should decay to 0 faster than this guy, like here. Here is example. You can see the blue circle are the singular values. You can see it decreases. It decreases to a very small number, very close to 0. So you can see this is our. You can see the green one is the upstairs here. It decays to 0 faster than the singular values. Because the decrease of this guy is faster than this guy. So for the signal projection, for the overall signal projection, it decays gradually. That means the useful information in these directions are very limited. You can see these directions, the signal projection, and these directions are dominant. So if we put here there is no noise, but if we put some noise, if we put the noise level is here. The noise level is here. because for these directions, the signal are dominant. Actually, the noise cannot influence these directions, but for these directions, the useful information is very small. The noise dominant. So you can see here, if we divide the noise by a very small singular value, the noise will be amplified. You can see here, the red diamond, they are amplified. These actually are the garbage for us, because they are mainly the noise, amplified noise, very limited useful information there. So the idea for the Tikhonov is that and actually the Tikhonov solution is a modified version of this solution. Actually, you can see here in Tikhonov, it puts a weighting coefficient here. It is a f. Actually, the f depends on the singular values and the lambda here. Actually, people use different methods to find out this lambda. I think for this question, the lambda is somewhere here. You can see if the singular value is much larger than the lambda, and the weighting coefficient equals 1. So the information at this location survives. But if the singular values are much smaller than the lambda, so you can see if this guy is very small, so this weighting coefficient becomes 0. So the garbage here are truncated because the useful information here are very limited. So we can truncate this amplified noise. That's the idea for the Tikhonov method. But we found our problem doesn't violate the discrete Picard condition. And so this is our problem. You can see, you can see the red one is the signal projection. You can see it is not gradually decreased. Actually, it fluctuates here. You can see although at these directions, the noise, the blank one is the noise. Although the noise level is very high, the useful signal is also very high. So we cannot truncate here. If we truncate here, we lose some useful information. So the idea is to put the measured noise into our wave propagation model. And finally, we derived a theoretical upper bound for the amplified noise. You can see in this figure, the blue one are the amplified noise, and the red curve is our derived theoretical upper bound. So you can see, yeah, it is well covered, the amplified noise. So if we know this theoretical upper bound, and probably we can determine one threshold. And if the upper bound here is larger than this threshold, we can tell, oh, it's a ill-posed frequency. And if the upper bound of the noise is lower than this threshold, we can tell, oh, it's a well-posed information. It's a well-posed frequency. We should use that frequency for our detection. That's the general idea for here, because we use the matched field processing. So matched field processing make use of the whole frequency domain instead of a single frequency. Yeah, so we can neglect some ill-posed frequencies. Yes. So you can see here we we test our scheme in this network. Here we put the noise, like the SNR is 10. You can see here if the lake is in pipe 1, pipe 2, pipe 3, pipe 4, we can localize them. And also we test it in this larger loop network. You can see we can localize the lake successfully, even though their noise. And this one is our ongoing work. And although actually this method has been developed for like 20 or 25 years, the theory has been very well established, and the theory also has been validated in the lab. But when we go to the field, we cannot find out the lake because there are lots of uncertainties there. Initially, we may think, oh, the pipe is an artificial structure, probably there, unlike the weather prediction or the groundwater flows. In the pipe flows, there are not many uncertainties, but there are lots of uncertainties. That's why we cannot deal with this problem using the traditional deterministic model. So now we are working on the data assimilation, and we wanted to combine the data and our traditional model to based on the Bayesian theorem to improve the accuracy in the field test. Hopefully, we will bridge this gap in the near future. Last but not least, I would like to thank our colleagues, the co-authors, like Professor H.F. Duan in PolyU, and also Professor Xun Wang in Beihang University, and also Professor Gedawi and Luati in HQST, and also Professor Ling Zhou in Hohai University. And actually, our research are supported by the NSFC and the Hong Kong Research Grants Council. And actually, this is only a very brief introduction of our work. So you can read our papers for more details, or you can contact me by the WeChat or email, and I'm very happy to answer any questions. Thank you very much.
Thank you, Dr. Cher. We'll now proceed to the Q&A session. Please feel free to leave a message to the chat room if you have any question regarding the webinar.
Maybe they need some time to write down the questions. In the meantime, while we wait for the questions, may I ask one question?
Yes,
on my own? Okay. My question is, I have several, but I want to focus on the main one. I see from the last slides that a very big deal here is to deal with noise, right? In your signals, it's very, very important. It interferes with your results. As you said, sometimes the problem is that the noise interferes in regions of frequency when you still have body of information, right? So you cannot just take away ranges of frequency, right? My question, this is the preamble. My question is, it seems to me, by this very awesome work you have presented, that you deal with noise as a synonym of complete uncertainty, right? That you don't know what's the origin or the external force causing this. But you know, there are some fields, for example, when you deal with imaging, for example, with nanoimaging, that nanoimaging is intrinsically related to noise because you can never slow down a molecule to take a picture, right? You can never do that. So what the people do in that field and fields related to that is that they model noise. there are models of noise, because noise, despite the word, is not completely random. There are rules for that. There is a classification of noise. So noise follows some trends. For example, some kinds of noise follow a normal distribution. So my point there is just to mention that, because there, if you assume or you have an idea what's the behavior of your noise, it's possible to carry out a deconvolution. Like if you know already what kind of noise do you have, there are ways to take that away, like to get a simplified version of your system without noise. And then people use that in other fields. My question is, have you considered modeling noise and including a model of noise into your framework? Maybe, do you think that would be useful?
Yeah, I think that's useful, because I think you are right. There are two different, there are two types of noise. The first noise is random, random noise. And for the random noise, probably every time we do the experiment, the random noise is there, but each time different.
Exactly.
Actually, now we are dealing with this kind of noise. We assume the Gaussian noise here in our work, but there is a second noise. We don't know they are there, but they are there. And every time we do the experiment, the same noise. I think there's some physical meaning.
Yeah.
Our model cannot include that noise. I think we can call it modeling error.
Yeah.
For that one, I think we will include in our the new framework, the data assimilation. That one is more like the uncertainty. Yeah.
Yes, and because the problem of noise is that you can understand if you kind of guess the source. For example, in my field, I work with pipes that tend to do flexural vibration, right? So they are a little bit bent, and you study that effect. There are many reasons for that to happen, especially when you deal with flows with multiple phases. For example, when you have a mixture like a slug flow, when you have a mixture of solid and liquid or liquid and gas, it happens that it causes a little bit of instability. So your pipe, even behind the ground, it could start just vibrating a little bit. That's another kind of noise. The funny part of that is that this noise only appears in a very specific range of frequency. I just wanted to comment on that to point out that, okay, I understood your question, your answer. Thank you so much for that. And I have one more question just about that. I understood, and it was very important that you need to know by start the structure of your network, right? You need to know how many pipes are there in there, the branches or the junctions, whatever. But for example, when we study a very old pipe network like this, 100 years old sometimes, do you think it could happen that the picture we have of the network is actually wrong or incomplete? For example, that it could happen that there is a portion of the network that is not included in the maps because people don't know, or the data were lost or something. My question is very simple in your framework. Is it possible to use this tool if you don't know completely your network? If there are uncertainties in the number of pipes or in the number of loopholes, is it possible to use it still?
Now it's impossible to use. We need a model now. We need a model, or in the future, we need the data to put it in a model to solve this problem. But now still we needed a model.
Okay, maybe you know that would be interesting, because sometimes tools like AI are capable. For example, if you ask an AI, okay, it seems that the solution to this problem of fitting data to is that we need one more pipe, but we don't know where it should be because the data are incomplete, right?
Yes.
Maybe we can ask an AI. Maybe an AI it could be fit with data from another networks, and they say, oh, probably this pipe unknown pipe or hidden pipe could be here in this portion. Maybe there is room for a lot of integrated work. It's really an amazing field, very interesting. I see many interactions with the many fields here. Thank you so much, Dr. Chu.
Thank you.
So we have the question from online. The first question is that will the PowerPoint be uploaded? So Dr. Chu, will you mind upload your PowerPoint? Or?
No, I think the video is recorded I think maybe you can visit the YouTube later on. Probably you can send a message to me. I will share the video link to you for the YouTube.
Okay. The second question is that the transient wave is generated by the sudden closure of the valve. However, the peak value may exceed the pressure standard of the pipeline. This is not allowed in real project. This drawback limits the practical application of this technology. So how can we produce a safer transient wave?
Yes, probably we have this kind of problem because the water hammer is quite dangerous if we didn't control it. Usually, but for our method is a active method. Unlike the noise, unlike the background noise, we cannot control the noise, but for the transient, we can control it. We can probably we can send a small a wave with a smaller amplitude to make sure the safety of our network. But make sure this smaller wave is enough for you to scan your target pipe. I think there is a balance. I think this point is also quite important in the practice. Thank you.
Okay, then if we have no more question, we're going to end today's webinar. So
Okay,
thank you, Dr. Cher, as the
Okay,
speaker
thank
of
you.
today.
Thank
We
you.
have prepared carbon credit certificates to you as a token of thanks. I'm sure all of us have learned a lot tonight and hope you all enjoyed the webinar. The digital attendance certificates will be sent to your email in 4 weeks. Once again, thank you very much for joining today's webinar, and we wish you all a good evening. See you all again in future events. Goodbye.
Bye-bye.